Ladies and gents, my name is Brandon Stover. Welcome to the How to Solve Climate Change course from Plato University. Causes, systems, obstacles, solutions to this global challenge is what you're going to learn here today. When you're ready to learn more skills, join us for free at plato.university. Let's get started with today's lesson. We'll have our expert guests briefly introduce themselves and their credentials for why they are able to speak to this topic.
So my name is Merritt Dailey. I am a PhD candidate at Arizona State University's Center for Negative Carbon Emissions. I work with Klaus, Lackner in the larger team, and we're building a direct air capture unit on campus there. I also do technical work for Carbon Direct. They invest in carbon removal and low carbon solution companies, including one DAC company. And I have been at this for about 2 years.
Can you explain to us what direct air capture is from a first principles perspective?
Direct air capture is a type of machine that chemically removes ambient carbon dioxide. So this is a machine that is built with the purpose of coming into contact with large quantities of air that contains CO2, which is all the air around us. And these machines are designed with chemicals that have a really strong affinity for carbon dioxide. So you could imagine the distribution of carbon dioxide in the air. It's measured by ppm. So it's something that you hear a lot about in the news and what's driving climate change. So you'll hear, atmospheric concentrations of CO2 are now, I think, 417 ppm. What that measures is within air, about 400 particles or units or molecules within 1 million are CO2. And so these machines, to do these DAC units, need to be highly specialized so that they'll come into contact with 1 million particles. And of the only 400 that are CO2, they're really, really good at binding with the CO2. So we can then do something else with the CO2, but get it out of the atmosphere. So that's basically how direct air capture works.
And why would this be a possible solution for climate change?
This is a good question. 70% of the United States, by polling, now agrees that climate change exists and is a problem. And so I would just say anecdotally in my own life, I have noticed that the climate has changed. I'm from Pittsburgh, Pennsylvania. We used to get snow every year. We used to get snow for Christmas. Now it's usually rain. We used to get fireflies all the time in the summer. I have hardly seen a firefly in 10 years. Every year it feels like we get a message, it's the hottest year on record, et cetera, et cetera. So what's nice about direct air capture is there's a lot of historic CO2 that was emitted from generations before us. So when my grandmother drove me to kindergarten in her 1975 Cadillac gas engine, when she turned on the car and started driving down the road, she emitted CO2. Part of that CO2 is still in the atmosphere, and it will likely be there for about 100,000 years. And what's unique about CO2 and other greenhouse gases, they're loosely triatomic. So most of them are 3 atoms that are bound together to form a molecule. And they are really, really good at capturing heat from the sun, collecting it, and then re-radiating it back down to Earth. And so the problem with that, obviously, is the more of these gases we put in the atmosphere, the more of the sun's heat they catch and then send it right back down to Earth's surface. So our global average surface temperatures get hotter. Why we should care more about CO2, there's a lot of greenhouse gases. Another one is methane. And you might have read somewhere that methane forces more warming. So it's better at radiating heat back to Earth than CO2 by about 80x. But CO2 lasts an incredibly long amount of time. So that's why we're bothering to capture CO2 via direct air capture. And so why direct air capture is a solution? First of all, it's targeting CO2, and CO2 is warming the planet. So that's why it's a solution.
And on the other side of this argument, why would it fall short of being a solution or not work to help solve climate change?
Yeah, this is a really great point. Why it might fail is that direct air capture is quite expensive. So It currently costs about $800 a ton. And if we need to remove 1 billion tons plus of carbon dioxide a year, and that's a low end estimate of what we should be removing, that would cost the world $800 billion. That's nearly $1 trillion, which is, a 20th of the United States' GDP. If I'm not wrong about, I think our GDP is around $20 trillion.
Yeah.
That I could be wrong about. I'm not an economist. Either way, that's a very substantial amount of money. And what sort of gets philosophical about this is CO2 historically has not been regulated. My grandmother, when she drove me to kindergarten, no one came after her for emitting CO2 out of her car. There are schools of thought. Klaus Lackner is really into this idea, if people want to follow up on it more, that CO2 is a waste and should be regarded as a waste. And so things like direct air capture, they should be paid according to the principle that they are removing a waste. The really difficult thing is, and this is another good point of reading for people that are interested, you get into a problem of the tragedy of the commons, because when you emit CO2, you're putting it into the atmosphere, which is shared by literally everyone in the globe. So one fact that I've always found really compelling is that within about 2 weeks, the atmosphere has mixed globally. So if I emit CO2 from where I live in California, and within 2 weeks, that CO2 might have mixed almost equally in the entire atmosphere. So this happens very quickly. And so, what people do in Bangladesh really affects how I could live in the United States. So we share this resource. And because everyone is sort of dumping their CO2 waste into this resource, it's really difficult to quantify or to force or put a price on an exact amount that people should pay to clean it up. And beyond even just finding a price, it's really difficult to convince someone that they should pay when maybe someone else, like their neighbor, is not paying to clean up this waste product. So the biggest challenge right now is DAC is expensive, and it's not exactly clear who will foot the bill.
Looking at the stakeholders in this problem and then the solution, who might benefit most with using DAC as a solution, and who might be harmed the most by using DAC as a solution?
Theoretically, because of what I said about atmospheric mixing, so if I draw a ton of CO2 out of the atmosphere in the United States, theoretically, that's a global ton that's been removed. It's not like it's only going to affect the weather in the United States. Unfortunately, 1 ton is really not going to have an impact, but you get my point. If the United States is removing gigaton scales of CO2, that would benefit people theoretically in Bangladesh or maybe on some coastal island nations. Although at 1 gigaton, probably not. We need something closer to probably 10. But that is more a question for climate scientists. There is an issue or a potential issue with indirect air capture of like a moral hazard. So that has been something that has held development back historically. Some groups have argued that direct air capture is a license to pollute. And so if I, as an oil company, say, I want to keep extracting oil, but I have this great machine that will allow the oil I sell to be net zero. So net zero carbon dioxide emissions, because I have this great machine that will suck out all the carbon that I'm emitting from it. People have argued that this is a lifeline to continue the use of fossil fuel extraction. So from that lens, it's possible that fossil fuel could benefit from it. Who is harmed? This is a really important question too, and one that I think needs a lot of further work. So there have been very, very few direct air capture plants built worldwide. One of them is in Iceland, and it's removing, I think, about 4,000 tons a year, which is not a huge amount. Some of these chemicals that are used in these plants are potentially toxic, and if they're not managed well, if they don't follow like a protocol, that could affect local communities. But they have not really yet been built to scale for that to really be tested. So there's a really great amount of work within the direct air capture community to focus on environmental justice and raise those potential issues before they could become problematic. So most new projects that are being cited require community engagement, community development, community plans, community buy-in for these plants to move into their backyard. But theoretically, if these types of machines can really scale, they actually could benefit everyone, especially if there is a equitable ownership structure. So there's a great article that I'll share written by Holly Jean Buck and two other students who argue that, I mentioned that CO2 is like a waste product, that DAC and these types of machines should be regulated more like a utility or a waste services system that could be run by local communities and owned by municipalities or even states. Because at least philosophically, this really is a public good. Like everyone suffers from climate change. They suffer unequally. Unfortunately, the people who have contributed the least to climate change are at present affected the most. And so there is a really good argument to be made that this type of solution should be very equitable in the way it's implemented.
To get a full understanding of direct air capture, could you explain to us how one of these machines work and then maybe how it scales to larger plants?
Sure. So there's a lot of startups right now, and there's a lot of different chemical pathways you can pursue. So I think the most basic idea is that you force air through either using a fan to pull in outside air and blow it across your system, or you allow the wind to do this. You force air to make contact with your chemical solution or your chemical system, it could even be a solid that will bind strongly with CO2. So CO2, as it behaves in these systems, is weakly acidic. And so most of these chemicals are basic because acids and bases will bond and react. There is one DAC company that's quite large. They're called Carbon Engineering. They're based in Canada, but they're building some large facilities in Texas. And their process, what they do is they use potassium hydroxide, which is a base that's in a liquid solution. So they'll take fans that just pull in air from the outside world. They'll push the air across their solution of liquid potassium hydroxide. The potassium hydroxide reacts really, really strongly with CO2. So basically, if it meets a CO2 particle, it's like, oh my God, I love you. And they bond really strongly. And after the amount of CO2 is saturated in a given cell, once the potassium hydroxide has bonded with the CO2, then they'll go through the next step process, which is called regeneration. Regeneration is historically really energy intensive in this space because, as you can imagine, if you have a chemical reaction that it really strongly binds together, it takes a lot of energy to break that apart again. And so carbon engineering has to use very high heat to break up the bond that it just made. And it sets up this bond so that it can reuse the potassium hydroxide and keep running cycles of CO2. And then once the bond is broken and there's CO2 that's been separated from the potassium hydroxide, you have theoretically a solid stream of CO2. What you can then do with that carbon dioxide, there's a lot of options. So a really robust climate solution is to keep that CO2 out of the atmosphere forever. And you can bury that deep underground. So the EPA is starting to regulate this and facilitate this type of burial. You need to use a class 6 well. There's, I think, only one or two currently in the United States, but there's a lot of project applications in the pipeline because of the Inflation Reduction Act. But that's one example of how a direct air capture process might work. There's a lot of other startups. So I'll also give a shout out to Heirloom. They are doing a kind of riff on mineralization. So they're using basically a type of rock that really strongly binds naturally with CO2, exposing that rock sort of crushed up to ambient air, and then forcing the CO2 to bond with the rock that way, and then separating the CO2 and burying the CO2 where it will never see the light of day again. I want to note that Carbon Engineering, Vicky Hollub is their CEO. And if anyone is sort of curious to learn more about this, she gave what I thought was a really, really interesting podcast to Akshat Rathi's podcast called Bloomberg, I think, Zero. You should be able to Google it and find it. And she her company is an oil company. It's called Occidental Petroleum. They have partnered with Carbon Engineering, which is the DAC company, because I believe that they probably have some long-term plans about being net zero oil, but they also want to use the CO2 that they capture from the atmosphere to extract more oil from underground.
Hmm.
So Vicky Holub has said that she considers burying CO2 to be a waste of a valuable resource, because CO2 is a valuable resource to basically pump into old wells, and the CO2 will push out oil from all the pore space within the rocks.
What energy are these startups using in order to pull apart those bonds if it takes a lot of energy to create the heat for that? Because then you would have, if you're using fossil fuel energy, then you're going to have a non net zero situation going on.
Yeah, so this is a great question. And I'm thrilled you asked it because I love the technology side of this. So this means I get to talk more about the technology. So carbon engineering, they need about 900 degrees Celsius. So this is really high temperatures to break up their potassium hydroxide and CO2. They use natural gas. So they'll fire natural gas to burn a kiln and create this big flame and then capture the CO2 from the natural gas burning. So they have a dual process where they need to capture CO2 at two different steps. I don't know exactly the amount of energy per ton they use, but it is a substantial amount of energy per ton of CO2 that's required. Other approaches have pathways that will use potentially a lot less energy. One of them is Verdox. So they're another DAC company that started up, and they use just electricity. So they have an electrochemical approach. So they basically have two cells, and by applying electricity within the cell, it forces CO2 to separate, and they can off gas the CO2 that way. And that could be, substantially lower energy per unit ton. Other firms are using heat, but just less heat. So rather than 900 degrees Celsius temperatures that Carbon Engineering is using, solid sorbent DAC companies, so this could be someone like Sustera or Climeworks, they're probably using closer to 100 degrees Celsius. So in those cases, you have the opportunity to use something like waste heat. So if Climeworks actually started in Switzerland, and their original plant piggybacked off of a plant that was burning, I think, garbage, and it had excess heat, and they would use that excess heat to run their regeneration step. So there's a lot of interesting things you could do. You could do geothermal energy. That particular area, regeneration, is a focus of a lot of the R&D and innovation within direct air capture.
For direct air capture to work, what innovation or policy needs to be built or put in place to make it an effective solution?
So the cost needs to come down a lot for it to be an effective, scalable solution. So you hear a lot of focus on about $100 a ton. So that means if DAC is now about $800 a ton, we need an eightfold plus decrease in price. So for that to happen, we will likely need two things. So DAC has kind of two broad parts of its process. One is the capture, and then the second part is the regeneration step. So on the first part, the capture side, we need better sorbents. So sorbents are the name of that chemical that is bonding CO2. And right now we have some good candidates, but they tend to degrade pretty quickly, in the environment. They bond with water. There's a lot of water in the atmosphere. So we need great chemical engineers, chemists building new sorbents that are really robust and have a high affinity for CO2, but that can regenerate quickly. And then on the regeneration step side, there's a lot of interesting innovation around making heat just from renewable energy. So getting to very high temperatures without things like natural gas. I think there's more innovation that can be done. I mentioned Verdox and their electrochemical pathway. I think there's a lot more innovation that can be done on electrochemical possible regeneration pathways too. But broadly, cost for DAC needs to really come down. And then you asked about policy. So I will give a shout out to the Inflation Reduction Act. This was Joe Biden's signature climate policy bill. It passed, I think, last August. And it is really hard to understate how transformational it has been in this space. So The Inflation Reduction Act, I think I mentioned before that there's been a question of, okay, fine, CO2 is this waste product that's warming the atmosphere, but who should pay? Because it's a problem that everyone sort of does. Everybody is releasing CO2 to different amounts. The US has released the most historical CO2 of any country. So we certainly have a high duty to pull some CO2 out, but it does affect everyone. So for the first time in the United States' history, there's been a price on carbon that you capture from the atmosphere through the Inflation Reduction Act. So before, if I ran this process, maybe some companies would pay me so that I could sell them an offset. Maybe they'd pay me up to $800 a ton. But the Inflation Reduction Act has in the tax code money that's bookmarked for every ton you remove as a direct air capture company, you get $180 worth of tax credit. So this policy was absolutely huge, and has really catalyzed a lot of investment in the space. There was also the inflation, I think it's Infrastructure something and Jobs Act. It's IIJA, I think it was. Congress allotted $3.5 billion to build new direct air capture facilities, which will really, really help understand things that drive costs. So it will basically allow a DAC developer to share in the cost of building these plants, which makes it much easier for them to actually get financing to build the plants. Because if the government's saying, I'll pay for some of it, it's a lot less scary for these financiers to write a check and say, okay, yeah, sure, I'll help you build this first of a kind machine that has never really been built before. That's also been really transformational. But I would say in terms of policy that we still need, there's not really a global price on carbon. The EU has something called the ETS, which has a floating price on carbon. It would be really, really great if that could have some more set pricing. And if things like engineered solutions were more clearly included in that. I mean, the premier policy choice most economists have said for years that we need is a carbon tax. That seems exceedingly difficult to pass just because of the structure of how our government works and the Senate, and the fact that I think something like 36 out of 50 states in the United States produce some sort of fossil fuels. And that means 72 out of 100 senators have some fossil interest in their state that they have to look out for. That makes Senate action like a climate tax pretty difficult to pass. But more policies that show DAC developers that there is money, government is willing to help pay the bill, and it's secure that this type of money, if they build a plant that could cost $500 million or more, that the government won't just, change the policy within a few years and they'll be out hundreds of millions of dollars.
What are the best 2 or 3 resources to learn more about DAC in terms of climate change?
So I think if you want to get a really good understanding of direct air capture and how it kind of fits into the whole puzzle of climate change, the IPCC published a special report on 1.5 degrees Celsius. So 1.5 is this really significant number for the IPCC and within climate change. It's a target that the IPCC has put out as the upper limit of warming that our world can do by emitting CO2 without a lot of really strong and bad effects. And in that special report on hitting that 1.5 degrees Celsius warming target, there is a section on negative emissions, direct air capture, and how direct air capture fits in with other negative emissions types. There's a textbook coming out on direct air capture. Jennifer Wilcox has a really great book on carbon capture if people are really scientifically minded. I think it's one of the best, and it does not shy away from the chemistry at all. So if you have an appetite for, molar calculations or anything like that, that's all in that book. I think another great resource is the Carbon Removal Primer. That tends to be a bit more readable. And that's also Jennifer Wilcox and her group of students and collaborators. I think that's just been recently updated as well, but I would check that out. I would also check out the article I mentioned written by Holly Jean Buck. She is a social scientist and she's doing a lot of the work. Because you asked about who stands to be harmed by direct air capture. This is a field it's a question that's studied a lot by environmental justice workers or environmental justice researchers. And people in the field, and she's one of them. So I would also read that article by Holly Jean Buck. I think it's in The New Republic.
Right now, you're speaking to passionate students who want to actually solve problems like these. What top 3 skills should they study so that they actually have the ability to do so?
For one, like identify what you're interested in and what you can bring to the table. So this is a huge problem that's going to need so many different stakeholders from so many walks of life and so many different skills. So if you are more technically minded, there is certainly a big challenge within direct air capture for people who like chemistry, mechanical engineering, process engineering, even environmental engineering to get involved and help develop new sorbents or build plants or build them cheaply or come up with efficient process designs. If you are more interested in policy or type, advocacy type work like that, there's a lot that needs to be done in Washington on the Hill, in local governments. A lot of local governments are starting to plan net zero targets. There's great ways to be involved with that. If you're really good at bringing people together, if you're really good with social media, we need activists in this space. We need people who are willing to explain why this is important. A lot of it is, I think a lot of the message can get lost in the technical jargon and sort of the science that tends not to be as easily digestible. If you're good at communicating, it would be amazing to have people who are willing and able to communicate more with the general public about this technology, why it's needed, some of the challenges, where it fits in, its pros and cons. So I would just encourage students to think really honestly and objectively about what they like doing and what their skills are and kind of how they can work backward from there.
Many different technologies we discussed today. Explore the different direct air capture technologies available. Compare their working principles, efficiency, and scalability. Share your findings with others.
Thank you for taking the How to Solve Climate Change course. If you want to learn the skills to solve this global challenge, join us for free at plato.university for exclusive content, extra resources, and actionable exercises with every lesson. This course was produced by Plato University, where students turn passions into purpose and learn skills to change the world. Learn more at plato.university.